warm welcome to the afternoon session of day 4, 6 days of FDP on Introduction to Machine Learning, Python and Machine Learning. I'd like to welcome Ketan and to start the session.
Good afternoon, everyone. Hope you can all hear my voice. Is it audible?
Yes, ma'am.
Okay. Is my PPT is visible to all? Okay.
Yes,
Thank
ma'am.
you. Yeah, okay. In morning session, I have explained up to how the hyperplane exists and how you can represent the d-dimensional space in a hyperplane. So the second thing we are going to see why we are going for optimization problem. So what is an objective of an optimization problem in respect to SVM, that is support vector machine results? It is used to maximize the margins between the hyperplane. So you can expand the margin space in your hyperplane and the closest data points from each classes, it is known as a support vectors in SVM. So you can define the relationship between the expanding of the region of hyperplane and the closest data points you for optimizing your model's performance. So this margin maximization is usually dealing in achieving the better generalization of new data, because a generalization exists if you are dealing with an unseen data or unable data. Your model should perform in an optimized way in order to ensure a high generalization of your model. So thus it helps in enhancing the model's robustness. So that's why we are going for an optimization problem. So second thing, what optimization problem we are dealing with here in SPM means we are dealing with convex optimization problem. Why we are going for convex? Excuse me. Why we are going a convex optimization problem means it generally minimizes the weight vector here. So weight vector is represented as W. So in hyperplane, in order to minimize the area, this optimization problem is expressed as minimize of half of the weight vector, the whole scale. We are going to take the squared normalization for the weight vector. So that's why it is represented as a double slash of W and double slash closed and squared, which and representing the length, and W is the magnitude of your hyperplane. So that's why we are minimizing. If you are minimizing this, it effectively maximizes the margin, because whenever the value of this one will be decreasing in a wider margin between the classes, it will be giving you the good optimization in your model. So this term, the wholly half of the squared vector normalization, it simplifying the computational power of your model. That's why if the computational power in terms of power decreases, it ensures the optimization problem remain in a convex shell, which makes you too easily solving the hyperplane vectors. So the third thing, constraints. So what are the constraints is need to be considered here? Uh, uh, generally the optimization problem is to find the maximum margin hyperplane, and it can be formulated as we have seen this. It can be formulated as like this, and after that you will be deriving the constraints based on the 2 points, that is x and y points on your hyperplane. This grade, it should be greater than or equal to 1. So this is also known as quadratic optimization problem. So why quadratic optimization problem means we are taking this x and y vector as a linear constraints, and these two can be solved using a Lagrange multipliers. We are going to see in future what are the Lagrange dual formulations. So where this represents the equations of the hyperplane as I have represented in the above figure, and this will be ensuring the data points from both the classes and outside the margin boundaries in your hyperplane. So what is a margin means? It is a distance between like this we will be representing, right? So these two are margins. So the distance between the hyperplane and the closest data points in the each classes, that is the margin. So while we are maximizing the margin and that ensures the hyperplane is optimally placed for the classification, it means that your model will be providing a higher optimization while you are using in the case for classifying your problems. So the second thing is the weight vector. It is represented as a W. So it actually determines the orientation of the hyperplane. It means that points scattered on the hyperplane. So it will be dealing with the orientation of the points in the hyperplane while minimizing this double normalization of a weight vector. It helps in widening the hyperplane spaces. So the third thing is bias, B. So it determines the position of the hyperplane relative to its origin. So this is the original origin. With respect to this original origin, it determines the position of your hyperplane. So while putting all together, so this SVM optimization problem, it can be simply stated as like this. And with respect to this one, it is based on the Lagrange's it is based on the quadratic optimization problem, and it is in a convection. So if these and that value exist, it shows that it has an efficient algorithm for finding an optimal solution. If this value achieves, your model is highly with a higher optimization. So why you are going for this normalization? Whenever you are minimizing this double normalization of the weight vector, the margin between the two classes will be maximized. These constraints ensure that each data point is classified correctly. So how we are going to solve this optimization problems? It is already I have said it is based on Lagrange dual formulation, that is Lagrange multipliers and dual optimization. This is the best solution. It gives the values of W and B that are defined within the hyperplane of all the classification. So here in while using the Lagrangian, the non-negative multipliers which are represented as a alpha, it should be always greater than 0 for each constraint in this. For each constraint in this should be always greater than 0. So the next one, how you will be deriving the objective function of the SPM. So the main objective of the SPM is to maximize the margin between the classes, as we have already seen. So the margin, what is the margin? Isn't it is a distance between the hyperplane and the closest points. So to achieve the maximization, this SPM is playing with the marginal values of your hyperplane, and this is one of the formulation for minimizing the norm of the double normalization, that is minimizing the double normalization by keeping the square for double normalization. So whenever you are minimizing this W, it will automatically maximizes the marginal value of the hyperplane between the classes. So the next thing, the objective function is same also here. So here you have to achieve the minimization of the vector weight vector form. So it is a squared Euclidean, that is squared normalization now of the weight vector. So why we are including this of means it is a mathematical convenience while we are taking the derivations. So constraints, correct classification condition. This is your correct classification condition for all I. So if you are representing this equation on the hyperplane, so it has to ensure there are two types of class points, positive and negative. If this y value is +1, it lies on the positive plane. If it is a -1, it will be lying on the negative plane. It means that beyond the limits of the opposite margins, and this +1 means beyond the margin. So then and there, the hyperplane equation will be like this for negative classes and positive classes. Complete optimization is same as the convex optimization problem only. So here the quadratic objective function and linear constraints formulations are defined like this. So such kind of a problem, it can be working efficiently, and these are solved using the convex optimization problems like Lagrange multipliers and dual optimization. We are going to discuss in future. So what are the key points to remember? There are uh, up to now we have seen how to maximize the margin and how to satisfy the constraints, and what are the support vectors and what are the closest points to the hyperplane that affecting the final position of a hyperplane. So how you are going to solve the optimization problem? So then and now I have said that by solving an optimization problem, we are going to use a Lagrange dual formulation. So here we are going to introduce the non-negative multipliers as alpha I should be all than 0. So this SVM optimization problem that can be efficiently solved using this method. So this is the method uh, in terms of alpha I, which can be solved efficiently with standard optimization techniques. So particularly by converting this one from a normal form to dual form, so it is very easier to solving your optimization problems. So that's why it is providing very flexibility for handling the complex data distributions. So the second thing, what is an objective function and constraints recap? So this is the main objective function we have taken for Lagrange's dual formulation. So the input vector will be W and B is the bias here. So to solve the above constraint optimization problem, so this is the Lagrange one. So this where W is the weight vector and B is a bias, and alpha represents the Lagrange multipliers. So and this is the Lagrange applies it applies the penalties of the constraint if the constraints are violated the hyperplane properties. So this calculation will be helpful in applying the penalties. So this is or Lagrange multipliers. It always should be greater than or equal to 0. So while coming to the derivation, we are going to take the differentiation for the weight vectors. So while maximizing the weight vector in respect to the alpha, the equation dual optimization problem, we are in dual optimization problem, we are going to compute a double summation of I and j data points with respect to the Lagrange multipliers on y plane and x planes. So in subject 2, we after simplifying this, we will be getting like this. In the case it's satisfying the Lagrange multipliers, which always should be greater than or equal to 0. Where this is a dual objective function, and these are the represent the dot products of the data points between the xi and xj. So the fourth thing, we are going to see interpretation and benefits of the dual form. Why we are going for the dual problem? So here only the subset of alpha only will be a non-zero. So that's why the points xi corresponding to the non-zero points, it is also known as support vectors here. So that's why the weight can be calculated efficiently by basing on decision boundary mechanism. So we as we represented in the SPM classifier, so with the equation of W star x plus b equal to 0. So one is here in optimal solution, so many of will be zero. So while considering the Lagrangians, it should not be zero. But here in while interpreting the SPM, so there will be possibles of alpha I will be zero. It means that the data points will be lying on the non-zero values. So if this property exists, it shows that it will not surely give you the optimal solution. So the second thing is non-linear extensions with the kernels. We are going to deal with some polynomial kernels or linear kernels like that here. So the dual formulation of Lagrange's, it makes it possible to apply the kernel functions, allowing the SPM to handle all the data that are linearly separable only. So it will not deal with the non-linear data. So by replacing with this kernel function, we can map the high dimensional space rather than using only the two-dimensional spaces. Solution of a dual problem. So here the dual problem, it will be providing it will be providing the optimal values of alpha I, which term to be the optimal weight vector. So the optimal weight vector can be calculated like this, where the bias can be calculated like this in the cases of alpha of S. So S represents the support vector should always be greater than 0. So as up to this, we have seen the dual form simplifications and kernel tricks flexibility. So there are what is a kernel trick means? If the data is non-linearly separable, so that is for non-linear classification problems means even it contains the soft margins, we can map that data into a higher dimensionally space where it becomes linearly separable. So this in this case it can be achieved using this kernel trick flexibility. So actually this kernel trick allows us to compute the dot products in the higher dimensional spaces, that is xi, xj, x y sorry x is it like that. So there are more than two dimensional spaces are included. So this kernel trick allows us to compute the dot product between these spaces without explicitly mapping into the data points. So the second thing is a dual formulation of an SPM. So this dual formulation, it purely based on the Lagranges, as we discussed before, the same thing here also. So constraints of the dual formulation will be derived as like this, whether all the Lagrange multipliers should always greater than or equal to 0. So how to maximize the dual objective means the dual formulation focuses on maximizing the function. Okay, it mainly focusing on maximizing this function by adjusting the values rather than or greater than or equal to 0. It will be adjusting the values or put inside a list. It should be always contained within the weight vector. That is weight vector. Only support vectors will having the non-zero values, as only these points will be determining the margins. So if any points lies outside the margin, if any points lies outside the margins like this, then the multiplier value will be always 0. So only the value points present inside the hyperplane will be having greater than or equal to 0. What are the benefits of we have seen this? Yes, also we have seen. So next thing is soft margin SPM classifiers. So actually the soft margin SPM classifiers and both allows some misclassification in order to prevent overfitting in case of underfitting problem. So this soft margin SVM will not be dealing with, especially in when when coming to their noisy data sets, so this soft margin SPM plays a vital role. So these key functions expanding the basic of SPM models to handle the cases where the data are linearly separable. So as in this case, it will not dealing with the non-linear separable data. So while considering the real world data, so these classes are always um, to be perfectly matching linearly separable. So in order to classify these kind of problems, so this soft margin SVM introduces the concept called slack variables. So slack variables will be represented like this. So this is a slack variable. In order to uh, handling the linearly separable data, so this slack variable is used. So it also should be always greater than or equal to 0 only, as same as the Lagrange multipliers. So role of regularization parameter. So C is a regularization parameter here. So if the slack variable is lesser than or equal to 1 means, so there will be a correct side of the hyperplane. So if it is always greater than 1 means the point is misclassified. So in case in these two if these two cases occurs, in order to prevent these type of cases, we are going for a regularization parameters. So this regularization parameter, it balances the two things. One is a margin maximization and minimizing misclassification tolerance. So this and this, it will be going to balance it. So if the C increases, if the higher the C increases, so there will be a penalties for misclassifications or more severely. So then and there, it will be creating a narrow margin but reducing the training error. In this case, it will reduces the error. So when there will be a lower C, that is small c, it allows you to the wider the margin and tolerates more misclassifications. This will be providing a better generalizations. So the next thing is non-linear SPM. It purely dealing with the not linearly separable data. When you are considering a data like not linearly separable, even if it SVM is containing a soft margin, you can go for a non-linear SVM in addition with kernel trick. Without kernel trick, you cannot go for a non-linear SVMs. So the basic idea is to mapping the higher dimensional features or higher dimensional space, whether it is a linearly separable, and then find separating a hyperplanes. So this next thing is feature space transformation. So the concept is behind here. This concept, this is the feature mapping. It is feature mapping is represented as pi of x. So the pi should be always, it depends upon like this. So it means a goal is to find the hyperplane in the transformed feature space. What are the kernels in SVM? So a kernel function, it allows you to compute the dot product between the higher dimensional feature space without explicitly computing the transformation. What is the advantage of using the kernel trick means? While dealing with the non-linear SVMs, without kernel trick, you cannot optimize the model. So while you're going for a non-linear SVMs, so for in order to reduce the computational cost, you can use this kernel tricks along with the non-linear SVMs. So this kernel function can be represented as k of xi, comma xj. It calculates the dot product between the feature mapping function, that is x of I dot y of x of j. it directly computing this with the help of the kernel trick. So there are types of kernel tricks or kernels are available: linear kernel, polynomial kernel, and Gaussian kernels are available, and sigmoid kernel. So the first thing we are going to see deal with the polynomial kernel. It will be computing the dot product between the kernel space features, where D is the degree of the polynomial. So it will be suitable for capturing the interactions between the feature. While you are dealing with a linear kernel, then k of xi comma xj equal to simply a dot product between xi and xj. This is the linear kernel. So a radial basis function, it is also known as the Gaussian kernel. So this is widely used because it is more flexible, and it has the more ability to create a complex decision boundaries. That's why going for the radial basic function, it is represented like this. It is purely dealing with the exponentiation of the xm and yi between the 2 points. So if your data is more complex, then you can go for RBF kernel. So the another one kernel is there, sigmoid kernel. So it will be dealing with the tan h function, that is k of xi and xj is equal to tan of h alpha. You will be taking the Lagrange function xi alpha into xi xj plus c. So this is an activation function of the sigmoid kernel. So how you can choose a right kernel? Since the parameters like C and gamma are difficult to, I think, these parameters you can feel in difficulties in tuning purpose. So in order to increase the performance of the SVM by creating a trade-off between these two parameters, there are two tricks are available. One is a cross validation, another one is a grid search. So while dealing with the cross validation, you will be testing the different types of kernels and parameter settings on the validation data. While considering the grid search, you will be exploring the grid between these 2 points and the kernel parameters in order to find which combination can be better for choosing your kernels. So the kernel trick, it is a technique, it is used to compute the dot product between the points in the high dimensional space. So while you are using the kernel trick along with the nonlinear SVMs, you can able to achieve a high generalization for your models. So the last thing we are going to discuss about the advantages of the SVMs. So the first thing, the support vector machines you are using for your research, it is very good classification algorithm. It is very powerful and versatile. If you are going for classification of images or finding a regression between the points or outliers detections, the SVM is very suitable. So first thing, it is very effective in high dimensional spaces. Why it is very effective in high dimensional spaces means it usually performs well in the cases if you are considering number of dimensions more than 2 dimensional spaces. Whenever the dimensional space is greater than the number of samples, this SVM will handle that situation very beautifully. So like they have the ability of handling high dimensional data by making suitable for complex data sets with many features like text classifications or image classifications or bioinformatics like that. And second thing is it is memory efficiency. Why it is memory efficiency means while dealing with a non-linear data using a kernel trick, so you can able to get within the less memory, you can train your model. So it is versatile with the kernel trick while using nonlinear data along with the kernel trick. So with this kernel trick feature, this SVM can model a complex or a nonlinear relationship between the data by mapping towards high dimensional space without computing the mapping explicitly. So common kernels like I have said the polynomial kernels or sigmoid kernels on RBF. These three kernels will allow you to get a greater flexibility of your model while you are dealing with different types of data distributions. So the next one is robust to overfitting. Why we are calling robust to overfitting means this will be giving you the proper generalization as it has generally a good generalization ability. So as it uses a regularization parameter C, I have discussed it before. While using the C, it will controls the trade-off between the maximizing the margin and allowing you to compute with some misclassifications. So this helps you in preventing the overfitting strategies, especially if you are dealing with high dimensional spaces. So in addition to this margin maximization principle helps a researcher to create a simple model with a higher optimization and works and creates an ability to work with more generalized models also. So it is very effective for binary classification problems. So why means it is usually effective in handling class imbalances. So with properly adjusting the points, it can handle the imbalanced data, such as by tuning the regularization parameters or assigning a different weights to the classes in real world scenarios like where there any one classes is underrepresented, so it can easily deal with that. So that's why it is very effective for binary classification problems. So good generalization ability I have discussed, and it is effective for outlier detections, and it will give you the unique solution. So we are using a convex shell, right? So this convex nature of SVM optimization, it ensures it ensures a unique and globally optimal solution in contrast to the models like CNN or DNN unit classifiers. These kind of classifiers can able to stuck with the local minima points, but this SVM doesn't do. So that's why it is very effective for outlier detections. So generally, these SPMs are powerful and powerful for dealing with classification and regression stacks, especially if you are doing or dealing with high dimensional or a non-linear small size data sets. You can go for an SPM. It is very good classifier while because it is using the kernel tricks and generalizations, they can able to provide robustness, flexibility, and interpretability. Uh, Please kindly unmute your mic. Someone have unmuted. Uh, Coordinator of pencil bits, kindly ask them to mute them. Aishwarya Morgan, kindly mute your mic, please.
My God.
Generally, SVM classifiers are computationally intensive and it is a little difficult to understand, but if you understand and use it for your research, it will be giving you the best results. And it will be providing high interpretability of your data, and it works very flexible as it is using a kernel tricks. And so, SVM in text classification, how it is useful. So, SVM is commonly used in text classifications like spam filter detections in emails or sentiment analysis while you are dealing with audio data sets. Like that, SVM is very useful. Um, and CNN classifier is also comparably good than SVM while you are dealing with audio analysis. And for image classification, how it is going means in cases of face recognition and object detection, like that, this SVM classifier is used. In case of dealing with the feature extractions of the pixels from the images or pre-processing of images or fingerprints, biometrics, this SVM classifier is used. So while comparing to the SPMs with other algorithms, it maximizes the margin and helps with the higher generalization. While comparing with the decision trees, it will be performing in the better in high dimensional spaces than decision trees, as decision trees will take you consuming of over time comparably with SVM, as you will be dealing with the step-by-step procedure like the step-by-step procedure, but this SVM it will be dealing with parallelly. So how to train your SVM? So what are the steps to training your SVM? First, you have to choose the appropriate kernel. So either linear or polynomial or RBF, what you have to choose. So next one, you have to choose the regularization parameter C, and you have to train your model on the data set. And after that, you have to optimize your model using an objective function. So this is the steps for training the SVM classifiers for your data set. And how you can evaluate the SVM model means these are the basic metrics: precision, recall, FI score, and accuracy of the basic metrics to evaluate your SVM models. And you can go for a cross validation in order to increase your generalization. You can go for cross validations. What are the challenges while using SVM means? It is computationally expensive when you are dealing with a large data sets. That is only one advantage in SVM. So if you are dealing with a high dimensionally space along with SVM, if you are using any kernel trick, you can also overcome this. And how to tune your hyperparameters. So the first, usage of regularization parameter, then choosing appropriate kernel type and going for a kernel parameters, that is RBM, RBF, or this parameter in kernel trick like that, regularization parameters. By using these kind of parameters, you can tune your SVM based on your datasets. While in the multi-class classifications, so there are two categories are there. In dealing with the multi-class classifications, there are two strategies: one versus one and one versus all. You can create only one classifier for two. If two pairs of classes available, you can create one classifier, or you can create a separate classifier for separate classes. That is one versus all. And these are the summaries of an SPM. As I already said, it is a powerful machine learning algorithm used for classification and regression. And along with the kernel tricks, it will be having a capability of dealing with higher dimensional spaces in order to provide a high performance generalization. And it works by finding a hyperplane that separates the data points into different classes. And thank you. So then and there, your fourth module is getting completed here. Any doubts in SVM? Any doubts, you can unmute and you can ask. Okay. Coordinator from Pencil Bits. Is there anyone from Pencil Bits? Okay, thank you for the wonderful session. Thank you for the opportunity given by Pencil Bits India, and also thank you participants for patiently listening to my session.
Yes, ma'am. Thank you all the participants for the session, and the participants are asked to fill the feedback form for day 2, day 4. Thank you, ma'am, for the excellent session.
Thank you, ma'am. Thank you. Shall I leave?
Yes, ma'am.
Yeah. Okay. Thank you. Thank you, everyone.